apart from spending time in the application security business and also focusing on cloud security, I'm a code scanning nerd. You'll see this in a couple of slides. I feel I've spent an in-proportional amount of time learning the various ways in which code needs to be interpreted and understood. That is a skill I can only use in my job. And I'm looking forward to sharing a lot of do's and don'ts and a lot of pitfalls of some of the approaches that we try to take here at Buzz. Let me also, in terms of housekeeping, if you want to track Buzz and how we operate today, you can check out our website at buzz.co. You can follow me on GitHub and my team on LinkedIn and Twitter. That's where we share most of our research findings and some of the progress we've made so far. So this talk is called Ordering Files for AI-Assisted Development. And we're essentially going to cover an interesting set of research initiatives we took here internally ever since starting Buzz about a year ago. And as often, I mean, if you are listening to this talk, you may not be surprised. One of the most promising applications of large language models has been code generation. We've seen this in our previous companies working on solving problems in the security space. And we're now taking that and scaling that up and generalizing some of the approaches that we've taken previously to see how we can help teams perform code reviews in the age of AI using these amazing tools. So this talk will get very technical very fast. So we'll start really putting up some basic premises to get us going, a few analogies that we'll use along the way. The first one is code grammar. So even before we dive into ordering files, and specifically in the context of code review, we should take a look at code and code grammar and see what it brings to the table. I mean, ever since I learned how to program, initially on Python, I love this analogy that coding is very much like driving, even before autonomous, and that structs and the grammar of Python can really serve as a set of traffic signals for us to be able to understand and read code. And this is a very simplified example where I took a bunch of traffic signs that we all know and fairly simply understand. And they all actually have within our code specific meanings in the form of structs. Input validation for a stop sign, where the input validation acts like a stop sign in code. It's ensuring inputs that are defined as criteria, as proceeding before errors and crashes. And you can look through these examples, not to spend too much time on them, but I think it's an interesting way to think about the unseen part of code. You'll see me talk about the implicit and the explicit areas of code. Even when it's not, kind of neatly displayed on a single file or on multiple files, code is going to have a lot of various grammar components that are going to take into account as code is either executed, interpolated, or compiled. And we'll talk about what those mean in a couple of minutes. Specifically, when I focus on AI coding, and this is everything with that has to do with coding agents and how we think about using frontier models to understand code bases better, and use these great capabilities of how these new generation of LLMs understand code to be able to perform coding tasks. And I really love this 4x4 grid. I use it all the time to kind of organize my thoughts on how we should or we could implement these LLMs for a variety of use cases when we think about incorporating LLMs into specific workflows within developer flows. So my x-axis goes between code completion, kind of very straightforward, give me the next components, help me complete this code that I've already begun to write. And all the way goes to the right side to code generation. This is where sometimes my starting point won't be existing code, would be an idea, as an example. My y-axis includes the use cases in which I want AI to have more control. This is where I can use things like agentic workflows to take multiple steps in order to plan, spec, and then evaluate and execute the code that I plan to write. And on the bottom, we have kind of the current mature model for copilots, where developers are in control. They can use tab to accept a recommendation, or we can refine through a chat interface what exactly we want the code to do. And you can see that grammar actually matters for all of these use cases. And the fact that LLMs understand grammar already help us, especially in this this bottom left quartile, where we're mostly focusing on code completion using copilots, and we're mostly relying on human in the loop to be able to enforce and provide the feedback that's required to accept results. You can see that as we progress to both generation and areas in which we want to AI to take more control, the use cases become more interesting in the sense of being able to use either past context or existing context in a specific code base or project to be able to provide additional coding elements. And this is where things get really interesting for grammar, because on one end we want AI to be able to take control, even maybe to write code better than us. But on the other, we wanted to continue and maintain the conventions of a past project. And the promise here could be one of a variety of interesting research areas. Two that we won't focus on today. One is reasoning models that can kind of create these chains of thoughts of different questions about how code should be composed before providing the eventual result. And the second one is mostly around increasing the context window. So we assume, and we've seen early results of that, that if we cram an entire code base to a model that's susceptible for that amount of tokens, we can generally ask it anything and get consistent results, and the model doesn't get lazy or tired, as you might sometimes find out when you use some of the commercial off the shelf or some of the smaller models on Hugging Face. Those are the two we won't be talking about today. We'll talk about an area of research that's slightly overlooked, and even you can think of it as kind of almost low cost, which is just changing the order in which we feed data into a model. So this has kind of semblance to this idea of a chain of thought, but it also utilizes the fact that we can use other tools to figure out code grammar before we cram it into our context window. If you think about it, today, grammar already makes all of our developer tools work. So when we look at our IDE, it uses a language server protocol, and it helps us go from definitions to references and navigate within our project based on the ability to identify these cross-node relationships across files for a variety of different languages. You can use plugins, you can use a local server protocol, and that's generally how you navigate within a code base in your IDE today. When you think about package managers, this is your NPM, most recent Ban, and Cargo and Maven, and everything that you need to get your project set up with required dependencies. It builds a dependency graph. There's different ways to build a dependency graph, but the end result is quite the same. We want to use the dependency manager's grammar to import a subset of packages that's required to the project and nothing more. Some languages do this better than others, and that's an area that we've already seen a lot of improvement when it comes to giving models only the correct set of dependencies instead of giving them everything that we've ever wished to import. My last example, quite non-trivial, is actually cloud, and my background in infrastructure is code. Infrastructure is code, languages like Terraform from HashiCorp, CloudFormation from AWS. They all use a graph backend that describes the different relationships between resources. That then enables me, when I want to make changes, to see only the incremental change without destroying elements of my infrastructure that aren't supposed to be impacted by a change. If you think about it, it's quite the most impressive or elegant implementation of grammar in our modern stack. It really makes changes much more seamless compared to when we think about application code. So what problem are we trying to tackle? We're tackling the problem of pull requests. Pull requests, whether we like it or not, are the main convention to introduce code edits to our existing code base. But code doesn't live in isolation. When we ask our peers to evaluate code changes from a massive project, we give them only a subset of files. We assume that they can see the matrix. That's how I call it. We assume that they'll be able to interpolate just as a compiler can or an interpreter can, the different downstream impact and the blast radius of a change. And for humans, it's not easy, right? If you haven't been at the company for very long, or if you aren't as proficient with the programming language and you don't really understand some areas of the grammar, then you won't be able to comprehend the entire scope of change. Maybe you're not supposed to. Maybe you're only supposed to understand that subset, but effectively, that's not really the case. Effectively, pull requests will often ignore the downstream grammar. They'll give you a subset of code to evaluate, and we'll kind of have our fingers crossed that other processes downstream, like our CI/CD, our integration, our build systems, will help us catch these downstream impacts that humans find it harder to extrapolate and evaluate. One last rant, or maybe two last rants, is possibly Git could have solved this, right? So if you think about Git logs and specifically commit messages, think about a world where we can constantly iterate on commit messages and constantly use them to anchor changes and make them our context or our grammar anchor for understanding changes within the scope of a commit or a PR. But just as my man David Beckham said, that's not really the case, right? If you open my code, this is probably the types of commit messages you'll see. We don't have sufficient tooling today, but we also don't have sufficient processes to help us make that commit message back and the connective fabric or connective tissue for code. There is an interesting area of that, by the way, if you're interested. The concept of stacking could be stacking combined potentially with AI. Maybe for an idea for my next talk is an area we're exploring to maybe bridge that gap as well. Okay, last rant, I promise. What do you think about reading a GitHub PR in order, right? If you think about pull requests, you're probably seeing them on GitHub. If I have to imagine, there's 4 areas within the GitHub PR tab where you would generally go to understand the flow of a change. You can use the description tag. That's where you have like this timeline of all of the changes that have occurred. You have your main description. You have all of the your checks on the bottom. What's kind of the merge blockers? Everything you probably need on a time based format. You don't see the code. That's not something you'd see there. You see all the interaction of your teammates. The second aspect is commits, and commits again. If we would have organized commits, and if your organization organizes commits in an amazing way, please let me know. But generally, commits are a good place only to see the incremental change after you've already reviewed a PR. I won't spend too much time about checks. Not a page that I like that much. It's where you go to see the results of your CI checks. Usually get thrown out to a GitHub Actions tab, then you have to go back out of order. But in 90% of the time, you'll spend your time in this A to Z sorted file change tab, and that's where most of us spend our time. That's where we look at code changes. Again, a subset based on a Git diff, and that's how we try to make sense of it. And to be honest, I think that's not good enough, right? I find it, again, my man, number 7, David Beckham, wants us to be honest. This process is difficult, and it's hard to continuously use these workflows to see and understand the linearity of a code change, because you do see only a subset of it on every one of these GitHub tabs. And that's probably the best way to describe our motivation for going on this journey. We felt like we can take Git and GitHub and the pull request process and dismantle it and rebuild it in a new pattern, a new order. And the way we wanted to do that is using automation that will essentially read code the same way that us as humans would read code. So the best practice for a pull request is actually to check out the branch, run it locally, and look at the debug logs and errors, and kind of test it out for yourself, and kind of go through within your IDE through the definitions and references and look through all of them. And that brings me to code indexing or code directionality. That's generally our starting point for this journey. So code indexing has been around for a while, right? So you've already seen this if you've been using an IDE for the past 12 years or 15 years. This is what gets you from point A to B within your IDE. Tools like LSP, the language server protocol that's maintained by Microsoft, the LSIF, which is an improvement on that protocol. GitHub has two projects that kind of go back and forth between indexing and references called StackGraphs and TreeSitter. SourceGraph has a great project that's supposed to kind of solve some of the problem that LSPs have. And most recently, we've gotten the addition of large language models. I'll specifically talk about OpenAI's 4.0 model, and I know you can kind of rant that maybe Sonnet 3.5 is better, but believe me, based on some of this empirical research, generally we've gotten the same kind of consistent results for this type of use case. But in general, what I wanted to show you is that there's generally three ways to look at this problem. The first one is LSPs, language server protocols. They're kind of the one-off approach, right? So given a symbol in code, these language server protocol, it's an open source, you can check it out in GitHub and the Microsoft website, will help you traverse your language's AST and reach the next area in which that code is either referenced or defined. StackGraph actually works very similarly. It's what powers some of GitHub's precision search, if you've seen it on the right, and TreeSitter is the same thing, but only incrementally. It can kind of run through the entire code base. You can kind of mount it with more and more context. The outlier here, and all of these are what I would call like static code analyzers. They have not a lot to do with AI. All of these on one side, and the other one is large language models. And large language models are in the same batch because you can essentially do the same thing. You can open your ChatGPT or Claude console right now, and you can insert either an entire code base or entire repo and ask questions about how code is defined and referenced in specific languages. And unlike these static analyzers that build out or output a AST, an abstract syntax tree that represents, to the best of its ability, the execution path of a given code language, it kind of works like your interpreter or compiler. It uses language to understand the definitions and references. So if it's visible, then there's a good likelihood the models will capture it. And we'll talk about benchmarking now, and you can see what I'm talking about. So this is kind of a early phase part of our research back in the beginning of 2024. We use Skip, which is the extension or the augmentation of the indexing protocol that's available through the Microsoft project. And we used it to analyze Java repos. And it's effective. It does a good job for a variety of kind of standard use cases. But as always, it's imperfect. We found a variety of areas in which we had expected this to be much more accurate. For example, local variable handling, which was severely limited. The other one was package structure tracking that was also somewhat foundationally flawed. We found it to output lines of 0 for some Java elements. We might contribute a fix to that as well. And despite our workarounds, it just couldn't work for all of the languages that we were interested in sorting and ordering. My second example is TreeSitter. TreeSitter is a very popular project. It's a great incremental static code scanning tool. It's used by a lot of security static analyzers, including my old team that uses a subset of it. And it's great at creating snapshots. And we sought out to benchmark it against a Rust project. Our project is kind of a combination of some core capabilities in Rust that's now augmented by the usual JavaScript and Python for specific use cases. Again, for some use cases, we found it was successfully able to parse the basic structs and fields, the field types. It helped us establish the reliable parent-children relationships that we had expected to get. But it was also somewhat flawed. The impl functions couldn't be mapped to their parent structs and found and intended to break the entire chain. We found multi-line use statements also caused identifier splitting issues in some cases. And essentially, we looked at different ways to combine something like a skip that's really good at specific languages, but it actually, for some languages, it runs the compiler or runs the interpreter, which we didn't really like, with tree-sitter to get some optimal results because there was some overlap. But you can see it's an imperfect, no silver bullet, right? Not an imperfect end result, and the static tools didn't really get us to where we wanted. And then we started to check out GPT 4.0. This work started a good probably 5-6 months back. And we had a benchmark, right? We had the benchmark of how the static analyzers are able to traverse through the AST in specific languages, and we were able to see what the gaps are. And we were initially pleasantly surprised. We found that a full spectrum of definitions was available, and the multi-language support was much better than we thought. I mean, think of these models as essentially being able to support any language. I would assume that even very new languages would get great results for everything like variable assignments, constructs, aliases, etc. But reference matching was the biggest problem. So what LLMs do not do is they don't traverse the graph, unlike the tools that I mentioned previously. They input a piece of code, and they will essentially read it, and we use the probabilistic model, the same one that they would use to write a beautiful love song. They would use that same probabilistic model to explain the code back to us as users. So by relying on LLMs only for that direct string matching, we actually failed to handle some of the most common patterns, like aliases, pluralized name, contextual method calls, and a few others. So unfortunately, this wasn't a great kind of end result for this research, but it did get us to a point where I think it's worth spending some time on. I call this the pull request grammar gradient, and I'll go to my last version of it because my time is kind of starting to run out. But it essentially breaks down the areas in which we found the different models to be very good at, or actually not as good as we expected. So there's 3 sections here. One of it is probably the most human or manual area, which is the review and suggestion human feedback loop. Second one is testing and feedback and fixes. And the last one is deploying the code into a production system and using things like integration and CI builds to troubleshoot it. And you can see that in each one of these sections, we found specific areas in which the deterministic model combined with the LLMs could actually make the difference. So let's take the bottom section, the semantics and conventions. Surprisingly, the area where humans are especially interested in or focused on, not the area where AI is the best in. Logical and syntactic correctness is actually an area where AI excels. Input a log, output log in from CI in a bash format, ask for the best way to fix it. You'll get a pretty accurate response. And the last one is coherence. This is where we use models to try to help us understand whether or not code will eventually impact existing artifacts in production. So this is interesting. We can take different types of attributes of how code eventually gets manifested into services and infrastructures and APIs, and ask AI whether or not they'll be impacted, whether or not they'll be making breaking changes. So that's what we saw. We saw that the human reviewer is generally good at the left side of this model. The AI reviewer begins to be very efficient on text testing and fixes, and actually outperform the static models when it comes to coherence. And there's a lot of more research that we have lined up based on this work. I'd like to shout out my colleague Hauser. This is his GitHub alias and his LinkedIn profile. He's been leading some of this exciting work. You can see some of the work that he did to understand large scale code bases using sequence analysis using a variety of these static and dynamic tools, as well as some of the more complex large code base research that he's been doing for the past few months. Yeah, I think that's generally time. Thank you for listening in.
Awesome. Well, thank you very much, Sky. That was a really, really interesting session. Yeah, I'll invite anyone to ask some questions in the chat, and we'll ask Guy to to answer those. Where would people want to? Where should people go, Guy? What would you say are the kind of like next steps for people to kind of get more involved?
I think I would really encourage people to test out the existing models with their existing code bases, both on the public consoles. Try to feed a file, a diff, your entire repo, and ask questions. Ask, Claude 3.5 Sonnet and see what types of results you'll find, and start to get the feel of where these models really excel and where the gaps are. And if you really want to geek out, I would really check out some of these static analyzers like Tree Sitter and Skip, and try to use their output as a potential input for your prompts. So, for example, ask AI to now help you figure out what's going to get broken in some kind of diff that was analyzed by something like a Tree Sitter, and see if you get better results compared to what you've seen previously.
Amazing. We've got a question in from Richard. Richard wants to see the world burn. He wants to know what's the worst ordering of the data you saw for model performance. Let's start with the worst.
Worst AI models. So probably previous generation of the OpenAI models, just before for O. It was very clear before 4.0 that the model wasn't even trying to consistently parse out common code structs like we see it parsed now. And now, we're like light years away from where we saw that about a year, maybe 9 months back.
Right.
Yeah.
And in terms of the best?
The best is probably, so there's two parts to that answer. We found that O1 is the best at finding or answering questions around the maintenance of a convention. So if we got O1 to understand, let's say the contract or the API spec of a program, it was the best at figuring out whether or not a change will generate a downstream impact that could result in a breaking change.
Yeah.
From interpretability and explainability perspective, this won't surprise anyone. I think Anthropic's 3.5 Sonnet is the best we've seen so far. It's incrementally good compared to the last version, and that's probably the model I would generally start with.
Yeah, interesting. And do you find much of a difference or any variance in local models to cloud models, or not much?
Oh yeah. We've tested some of the small scale models, the massive instruct models, and you can't compare. It's unfortunately the commercial models in this type of work, where context is kind of multivariant. It could be a JSON that describes an AST, a diff that's kind of written in kind of a Git output, and code that could be written in anything from a YAML to a Python file. Unfortunately, the open source models are not as good as the commercial ones.
Yeah. Okay, makes sense. I have a question from Min, and I think this is probably we can answer this, specifically from your own experience. But I think this is kind of like fairly general question in terms of general usage of LLMs. Any privacy security concerns for feeding company code into models?
Definitely an area of interest in my past life. I'll first state the obvious. I think, given the level of efficiency we are bound to get from these models, especially for coding, I think it's inevitable that we will take on some of that exposure over time. I've worked at large companies like Palo Alto Networks that currently I've learned use Sourcegraph's Cody. If Palo Alto Networks have done the research modeling and found out that the lemon's worth the squeeze, I would definitely advise. And everybody on my team is already knee deep in copilots and cursors and everything, and are just 10x better.
Yeah, and I'd probably just add to that. Talk to your own legal teams as well. If you're working for a large company, talk to your own company's legal teams. They will very likely have advice for you in terms of what you can and can't use in that space as well. I think we're out of questions. I think we're out of questions now. Guy, why don't we let me move your session off screen. Thank you very much, Guy. Really insightful, and actually a very, very interesting session, which is truly, truly practical in terms of how we can actually get the best and the most out of what we have today. Of course, LLMs and so forth will get better and better and better over time. but we always need to get the most out of that. And I think the ordering, the prompts, the context are just key for us to understand how to get the most out of these systems. So thank you very, very much. Very, very good session. Thank you.
Thank you, Simon, and shout out Tesla team for putting this together. We don't have enough opportunities to geek out about these sorts of things, and it's really where the world's heading. So great initiative. Keep it coming.
Thank you so much. Appreciate that.